Hello everyone, welcome to the recorded video lectures of CY 4301 Quantum Chemistry. So you all know the situation very well that due to this pandemic outbreak, we are all locked inside our home and we cannot attend our schools. And NIT Rourkela, however, started its educational lecture sessions. So today we will start with the first lecture on CY 4301 Quantum Chemistry. And so the things work like this way. We will have recorded lectures which I will try to upload them in YouTube time to time. And after every 2 or 3 lectures, you will happen to see me, or means you can interact with me through Microsoft Teams, say after 1 or 2 lecture. And then whatever queries you have, you can directly ask me and I can answer. And about the details of the syllabus, how many times we meet, and what are the procedures for attendance, and what are the different weightages, detailed syllabus, question patterns, tutorial sessions, help sessions, and anything else, any technical details about the course curriculum and course activities can be answered through Microsoft Teams. So this is the purpose of this video, is to reach out the lecture materials. Okay, so you can hear, so you can see here, so this is an entirely homemade setup, and so I will be trying to record my lecture videos in traditional manner so that it will be easier for you, and I will definitely try to upload them in YouTube, so you can directly go to the YouTube and can see the lectures, and also if possible you can download it from the YouTube. Okay, so I would say that in this course, CY 4301 Quantum Chemistry, this is a 4-credit course, and in this course there are at least 8 to 10 chapters to be covered. So we start with the first chapter, that is the historical background. So the purpose of this chapter is to have an idea how chronologically the subject quantum physics or quantum chemistry developed from the classical background. So why are we learning this? We are learning this because it would give us a perspective to understand better that how the classical concepts slowly transformed into the quantum concepts. So we will start with in an era near about the late 19th century. So late 19th century means say in the period around 1880 to 1900. So in that era, surprisingly, many physicists believed that there are no new things to be discovered in physics. So that was a very bold statement. You see that physicists believe that physics had come to a point where nothing new to be discovered. Every new principles had been discovered already. So what are the new things to be done? Only the existing experimental procedure needed to be improved. Other than that, concept-wise, there are no new science to be discovered in physics. But it was a great irony in the history of science that exactly from the year 1900 onwards, that means during the time period 1900 to 1930, in those 30 years, the subject physics underwent a revolution. So that revolution is also known as the earthquake of physics. So those 30 years, something very unprecedented took place that actually shook the foundation of the classical physics. So it was also known as the era or the earthquake that shook the classical physics. So now we will take a look at what exactly happened in those 30 years in a kind of chronological manner to understand that the classical physics, so that the statement that there are no new things to be discovered in classical physics failed. Okay, so let's take a look at that. So let's try to understand what were the reasons due to which scientists believe that there were nothing new to be discovered in physics by the end of 19th century. That means at the beginning of 1900. So let's take a look over the development. So by that time, Newtonian mechanics was fully validated. Jules Carnot Gibbs together developed the concept of thermodynamics. The subject was totally developed. Then Maxwell and Boltzmann together they developed the subject statistical mechanics. And then due to the work of Young, Fresnel and Huygens, it was well understood that the light behaves as a wave. So the wave nature of light, the interference phenomena was totally known. And Faraday, Maxwell and Hertz, they together discovered the principles of electromagnetism, and not only that, people understood that the light also follows the electromagnetic theories. The electromagnetic nature of light was also established. So these are the few major discoveries, or this is the total body of accomplishments that constituted the subject called classical physics. Okay, so now we will take a look chronologically that what was the problem with this sort of classical physics. So as I have already told you that during the era of 1900 to 1930, physics underwent a massive revolution. So in other words, this is called earthquake. Earthquake in physics. So that took place during 1900 and 1930. So what happened was that physics underwent a set of profound discoveries, and those series of discoveries led to the establishment of a completely new subject, and that is called the modern physics. And the modern physics was basically stood on the shoulder of a subject called quantum mechanics. So the single subject, quantum mechanics, changed the course of the physics forever. In the years to come, the quantum mechanics affected not only physics, but chemistry, biology, and engineering and technology. So the branch of the quantum mechanics that deals with chemistry, or in other words, the part of quantum mechanics that was used to understand or explain the basic chemical principles is known as quantum chemistry. And this is a subject that we are going to study. So now let's take a look that around the year 1900, what were the things at that time going on so that the first feeling that the classical physics was not adequate to explain everything people knew at that time. So let's take a look back to some of the chronological events that happened just right before the era 1900. So let's take a step back and let's go behind a few years before the year 1900. Now let's take a look on the series of events led to the discovery of the modern physics. So you see, in the year 1895, William Röntgen discovered one of the most important physical phenomena, that is the X-ray. And then in the year 1896, Henry Becquerel discovered radioactivity. And then again, in the very next year, J.J. Thomson discovered electron. So he discovered, or he found out that electron is a subatomic particle and its charge is 1.6 times 10 to the power minus 19 Coulomb. So all those three discoveries back to back from 1895 to 1897. So within these 3 years, three groundbreaking discoveries were made, and all those three fell into the domain of classical physics. So by the year 1900, people had understood one very important point, that the atom is far more complex than it was thought to be. Why? Because you see, X-ray is an atomic phenomena, radioactivity is an atomic phenomena, and an electron, a subatomic particle with the negative charge, stays in an atom. So how one can explain all those three physical behavior, and of course the nature of the electron and how electrons are arranged within the atom. So all those, how can one explain within the atom? So the answer lies within the structure of the atom itself. But unfortunately, by the time, that means by 1900, nothing about or nothing detailed about the atomic structure was known, and so people realized that of course atom is far more complex than once it was thought to be. So there are certain hidden phenomena going on inside the atom. So, but still, even though with the achievement of these discoveries, right nearing the end of 19th century, people still thought that there were nothing new to be discovered in physics. But then, as I told you earlier, that from the year 1900, the earthquake started. So the question is, what exactly happened in the year 1900? So, what was the beginning incident of the earthquake? So, we can write that here. Beginning of the earthquake in physics, of course. So it happened in the year 1900. Now, in order to understand this event, what happened in 1900, we have to get back to one of the physics classical problem, or one of the old problems of physics, and that is called the problem of black body radiation. So what is black body radiation? Then we have to spend a few minutes on that to understand. So here I will try to explain the concept of black body radiation in a very short manner. So whenever a material body is heated under high temperature, so it tends to give off the radiation in terms of electromagnetic waves, that means light. So the radiation that are coming off, they tend to have all the frequencies. So that means they can start from the violet end to the red end. So all the frequency spectrums of the Whipjier are supposed to be within the radiation. So that's why it's called black body. Black means everything, it is all the frequencies, all the range, the entire range of the visible spectrum is being emitted. So that's why it is such type of radiation is called black body. So it is often related to the celestial objects like stars and suns, etc. So I will give you a very common example like a stove. So whenever you have ignited a stove, the burning stove at lower temperature, it first gives you a reddish light. Then with the increase of temperature, the light becomes intense red and then intense white. After that, finally, it becomes blue. Means the radiation that are coming out is of shorter wavelength, higher energy, and high frequency. So this is the graph plot by which the radiation, the distribution of the intensity of the radiation with respect to the different frequencies has been plotted. So how can it be interpreted? So it can be interpreted like this. So you see all the emissions, means all the frequencies are being emitted from the lower region to the higher region. But if you increase the temperature of heating, so this is T1, T2 and T3, the more you heat up the body, the maximum emission, that is the emission maxima, you are getting from the body will be shifted to the higher frequency region. So you can see, so at this body at a much lower temperature, maybe it is emitting in the red zone, and slowly it is with increase of temperature it is shifting towards the blue zone. So we can always see that with the extent of higher temperature, the maxima shifts to the right side. So here T3 greater than T2 greater than T1. Now this phenomena was known at the late 19th century. So as far as I remember, in the year 1897, a scientist called Wing, he did some fundamental research on the black body radiation, and he presented this kind of graphs, and he tried to explain the basics of the black body radiation. But such kind of observation at that time was very hard to explain in terms of a mathematical model. So the idea is how one can explain mathematically or using a formula, how one can explain the nature of this graph. Of course, the formula should come from the basic principles of physics. So what happened next, that just before 1900, the year 1900, a couple of scientists known as Rayleigh and Jeans, together they proposed a physical formula to explain the black body radiation. and their theory was known as Rayleigh-Jeans theory or Rayleigh-Jeans equation. So what was that equation? So let's take a look here. So here we go. I have written the mathematical formula proposed by Rayleigh-Jeans in the 19th century. So let me explain it. So in the left hand side we have a variable rho. Rho is called the radiation density, and this is a function of frequency as well as the temperature. So rho as a function of frequency and temperature d nu, that means the infinitesimal change of rho is equals to 8 times pi multiplied by kb. So kb stands for the Boltzmann constant into multiplied by the absolute temperature divided by c cube. C is the speed of light. Everything multiplied by mu square, that means the frequency square d nu. So that means this function rho mu t has been equated with h by kt over c cube. So Rayleigh and Jeans proposed this theory from the very basic understanding of the classical physics. So there have been few assumptions. So once you relate the assumption logically, rationally, one after another, so you are from the knowledge of 19th century physics, you are tend to arrive at that condition, means at that equation. So what is I? So I is the intensity of the radiation, and we can think about that I is proportional to the radiation density. So that means the more is the radiation density, more is the intensity of the radiation. So now let's take a look at how good was the Rayleigh-Jeans theory. So in the 19th century, the Rayleigh-Jeans theory, if you take a look at the equation, so in both sides the d nu part is common, so we can neglect that. So a variable rho mu t is equal to h, pi is a constant, Boltzmann constant is a constant, divided by c cube. C is the speed of light constant, and at a particular temperature the t is also constant. So suppose if you are doing that blackbody radiation study under a particular temperature, say either T1, T2 or T3, the T is constant. So what is left? So we can tell the variable factor rho, we can write this equation in terms of some constant called z multiplied by mu square, as if the relationship is something like that, and this relationship can be equated to y is equal to ax square. You can see that. So you can very much relate to this equation y is equal to ax square. So what is that? Yes, it is the equation of a parabola. So if this equation needs to be fitted with this one, how would it look like? So of course, if we plot rho versus nu or I versus nu, the theoretical graph plot, so this is theoretical. So the theoretical graph plot would follow the right hand curve of a parabola like this. So it won't converge, means it won't follow the experimental outcome of the blackbody radiation. So here at the left hand side, that means at the near infrared and red region, the graph means the theoretical prediction up to this much, this n works pretty well. But after that, once the frequency enters into the blue or UV region, there happens to be a significant divergence between theoretical and the experimental outcome. So that part, that means in the UV visible region, or in the near UV region, since the theoretical prediction completely fails, so that phenomenon at that time was known as the ultraviolet catastrophe. So what was the problem in that? So the problem was grave because although at the end of 19th century, the beginning of the 20th century, in the year 1900, people understood, physicists arrived at a conclusion that there are nothing new to be discovered in physics, yet there was one small little problem, that was the blackbody radiation, which from the classical theory of Rayleigh Jeans could not be explained. Okay, so that was the beginning, that was the first observation at that time, that well, there is at least one problem that classical physics could not solve up to that time. So what happened next? So that we are going to discuss in the next lecture. We are stopping it here today because this is our first online video recording, and after this lecture I have to compress the video and I need to upload that on YouTube. So let's keep the first lecture a little bit condensed and smaller on experimental basis. Let me see how well I can upload it in the YouTube. So if everything goes well, so from the next lecture we will have it a little bit extended session. So after you see the link in the YouTube, you watch it, and please feel free to give me your feedback. That means whether writings are legible, whether my voice is completely audible, or is there any other problem or any technical or any content related issues. So please get back to me, and I will be very happy to answer your queries over online video conference. So till then, goodbye, and let's meet for the next lecture, lecture 2, which will be uploaded very soon. Thank you. Have a good day. Bye bye.